So this lecture is on view materialization, which is the third technique third technique for improving query performance in a data warehouse. Earlier modules, earlier lectures of this module, we have looked at aggregation and partitioning as two strategies, and this is kind of generalization of aggregation, because aggregations are also implemented as metallized views. So I'll be talking about view metallization, the concepts, and some examples of view metallization, and what kind of issues it poses on the administrator of a data warehouse, and how it helps. Basically, first we'll talk about how it helps, and then we'll look at the issues involved and how do we handle those issues. So let me begin. So the topics listed for are query modification, then we'll talk about view metallization as a concept, and how to exploit metallized views to answer queries. So this will come the third question will be answered as we go along. So, and some examples I've taken, and these examples have been taken from the Database Management System book by Raghu Ramakrishna, 3rd edition, and you can refer to that for some more details. And I have towards the end of this lecture, I've put some exercises also from the same book, so you can try solving them. So first, let me talk about query modification. So this is basically, I'll have to switch off the video so that you can. Yeah. So query modification. So what it talks about is the conventional view that we create in a database environment, and I'm sure all of you are familiar with the concept of views. So let me just give you some points. So views are actually virtual, and they are not like whatever view you define. They are not actually stored in the database. The result of that view is not stored, or the tuples that qualify for that view is not stored. Say suppose I say select star from students where CGPA is greater than 8, right? So what it does is that it does not store the tuples that qualify explicitly in the database. Only the view definition is stored, and but from a user's point of view, any user can query a view just like it queries a normal conventional table. So when a view is queried, it is actually executed against the database. Its definition is executed against the database, and the results are shown to the user. So there are many benefits of this approach of views. So one of them is that whenever you query views, right, you will always get the latest or the current data, because the views are executed at runtime or at query time, right? So after the query has been executed. So the same concept has been illustrated in this example. So suppose I have created a view called as regional sales, and it does what it is an aggregation. No, sorry, it's not an aggregation. It's a category-wise sales of state, right? So what we do is we write this query, we define this view. So you can see it is a join between 3 tables, where I'm taking category and sales from sales, and state from the location, and from products P, sales, and location L, where this is equal to this and this is equal to this. Is a join condition that I've imposed, right? So this is a view that is created. Now I'm trying to do a query which is an aggregation, right? So what I want to do is I want to do a sum sales, right? Okay, so which is r dot sales, which is from the regional table, a regional sales table, a regional sales view. So this blue is a view, right, as r group by r dot category and state. So I'm doing a group by with respect to category and state. So the ultimate thing that I'm going to get is a state wise, category wise sales figures of the store. right? So now as soon as I put this regional sales in my query, right? Okay, so what happens is the system would do what? It will replace this blue by this blue part, right? So this whole thing will actually be replaced and it will come here, right? So you can see that select, actually this is the name, so this part. So you can see that whole of this has come here and rest of the query remains as it is, whatever is there. So this is known as query modification. So what modification is done? Basically the view name is replaced by the view definition. So view name is replaced by its definition. So that is the modification that is done by the system. And the view definition, now the question is that where this view definition is stored. So view definition is stored in the metadata. So I refer to the metadata. So when this query is parsed, right? So when this, I'll use some other color. So I'm using, oh, sorry, not red. Red is already there. So let me use yellow. So when this query is parsed, right? So what happens is that it looks at all the database objects that are there. So it will look at regional sales, right? So it will see that this regional sales is not in the tables list that you have created, but it will be found in the views list that you have created. So it will go and see that it is a view, and then once it knows that it's a view, it will go to the metadata and fetch its definition from there and replace this name of the view by the view definition. So this is how it is done. But in this whole process, so this another point that is highlighted in this slide is that evaluate on demand. That means whatever tuples qualify for regional sales, they would be evaluated at runtime using query modification. So everything will be done after the query is executed. Okay. So it is just like when you go to a restaurant and you order a dish. So all the things that are required for the dish, or all the preparations that are required for the dish, are carried out only after you place the order, right? So it is like this. I'll come back to this example again later in this presentation. So Metallized Views, as I told you, I've discussed most of the things here already in the previous slide itself, right? So what happens here now is, so I'm now talking about Materialized Views. So what are Materialized Views? So I'll explain that one by one. I'm using some concepts of views itself. So conventional views, as you know, are virtual. That means they do not have a real existence. Their tuples are virtual, that is, they are not stored explicitly in the database, but they can be computed at any time I need them. Only definition is stored in the metadata. I've already discussed this. View definitions are executed during runtime, that also I explained. And if views are complex, the queries using them will have large response times, right? So suppose I say a query, select star from view 1, and view 1 is actually defined as join of R, S and T, and R, S and T are big relations. So you can see that if I do a query select star from view 1, then what would happen is that this join would be executed. This is a kind of a join between three tables, or multi-table join. So this join would be executed, and then once it is executed, the result will be shown to the user, right? So that's what I have mentioned here. If views are complex, any query using them will have large response times, and this is not a desired situation in a data warehouse OLAP environment where the amount of data is huge, because we are in a data warehouse environment. We are dealing with huge amounts of data, and the queries are complex. So it will take a very long time to produce this result, R join S join T, right? Now let me give you a situation that I have already, so instead of a view, I have created what is called as a metallized view, which is R join S join T. Now what does this mean? This means that I have pre-computed, when I put the word materialized in front of a view, so instead of saying create view, I'll use the DDL called as create materialized view, whatever, say MV, as select star from R, S, comma, T. Okay, so this basically tells me that I'm trying to join these three relations as in the view, right? So I've created this view. Now once I say it is a metallized view, that means I've already pre-computed R, S and T. Join between R, S and T. So now when I run this query, so let me use another color so when I execute this query, right, so instead of saying view 1, I'll say metallized view. So select star from metallized view. So now this metallized view MV is already pre-computed. So this query will be answered within no time, right? So this query will be answered very, very quickly, so that you don't have to, because we are not doing any computation, or we are not executing any query actually once the query is issued. So we are just taking the result from the materialized view, which is just the opposite of the conventional view. Here its existence is not virtual, its existence is real. So that means what? That means its tuples are explicitly stored in the database, right? So I move away from the conventional concept of a view in a database and move towards what are called as materialized views, right? And there I store the results of this join explicitly in my relation, in any relation, right? And it is called as a materialized view. Now you can see, now the problems with this is that what happens if there is an R. So I'll explain this in the next slide. So let me first conclude the introduction part of this. So a view whose tuples are stored in the database is said to be materialized, right? And materialized views provide fast access, like a very high level cache, because here the tuples, you don't have to carry out any computations. I know that R join S join T is already there with me. I just have to pick it up and give it to the user, right? So it acts like a very high level cache, but it requires to be maintained as the underlying tables change. So suppose I have a materialized view which is a join of, say, suppose two relations only, R and S. So I have defined a view, materialized view, which is join of R and S. Now suppose there is a change in R, so R changes. So what I have done is, this materialized view will be like a table, and the tuples would be stored here. Whichever tuples qualify for this view will be stored here. Now R changes. So when R changes, so if R changes, so what happens? MV also changes, right? And you have a copy of this data, or you have the tuples in this, so you have to go and change this tuple or change MV in some way, right, according to what changed in R, right? So what will happen is that you may have to modify this MV according to the changes in R. Similarly, S can also change, or both can change. So how you are going to maintain this this copy of data that you have created through a materialized view, right? So that is what is called as maintenance. So every materialized view would need some kind of maintenance, but we are ready to do this maintenance because materialized views help in reducing the response time of complex OLAP queries, right? So that's why we don't worry too much about maintenance, right? And in fact, another aspect is that in a data warehouse environment, we are not too much concerned about currency of data. Even if the data is 1 day old or 2 days old or last week's data, we are okay with it, right? Because our refresh cycle is always like a day, it's a daily refresh cycle or a weekly refresh cycle. So we are not too much concerned, but at the same time, we must, if there are applications which require currency of data, so we need to make sure that all the views, all the materialized views that we have in our database or in our data warehouse are actually current. So we'll talk about that. So Metallized views. So continuing with the introduction part of this. So pre-computing some important. So I'm now trying to uh, kind of tell you about what kind of views we should materialize. Although it's a totally different concept, but here I'm just qualitatively giving you some idea. So pre-computing some important, expensive, and frequently required results. So that is what we try to pre-compute and store, right? I'll give you a nice analogy for this, and should be based on expected workload. And it is just like doing some prior preparation for dishes in a restaurant. So if everything is done after receiving the order in a restaurant, the waiting time of customers will be more, right, or will be high. Better to do some prior preparation to minimize waiting time. Read response time of queries. So it is just like, I know, so in a typical restaurant, when you go, right, and when you order a dish, right, so some prior preparation is already done for that. Say the curry is ready, only you have to put the ingredients now, right? So, and the dish comes out within few minutes. Okay, so how? So this would depend on what kind of dishes people have been ordering in the past, and which particular dish is popular or is in great demand. So you will accordingly do the prior preparation. Similarly, in a data warehouse environment also, if some kind of queries are very frequent or very important or which are very expensive, expensive means that their computation time is too high. So we'll try to reduce their computation time by pre-computing some part of it, right, and storing it as a materialized view. So that is what we do. So it is very easy to understand this concept of materialized view using the concept or using the example of a restaurant that we have been referring to right from the beginning of this course, right? So where we talked about presentation servers and the staging area, right? So here also the same concept can be used to explain the concept of materialized views. So you can see here that if you go to a restaurant where when you order, only then the entire dish is prepared. There is no prior preparation. So right from cutting the vegetables, preparing the gravy or the sauce, whatever it takes, right? So everything is done, right? After your order is received, so then your waiting time would be high, right? So we want to, in data warehousing, we want to cut down on the response time of queries. So we have to do some prior preparation. So this is a way to do it. So issues, so these would be discussed as we go along. So which views should be materialized? Now you cannot possibly materialize a view for each query that comes to you, because that would blow up your space requirements, right? So you cannot possibly materialize every view that you want for every query that comes in, right? So you need to be selective. So how do you do this selection? So that would be discussed in the next lecture, that is on selection of views to materialize. And then given a query and a set of materialized views which can be used, materialized views, to answer the query. So how can we actually replace the database objects in a query by materialized views so that the query response time is reduced? So how do we do that? And then comes the question of maintenance or refreshing the materialized views, right, based on the changes made in the underlying tables. So this would be discussed in module 7.6, recorded lecture 7.6.1, and how can we do this maintenance in an incremental way. So this would be discussed in 7.6.2. So let me try to give you now some examples of materialized views. So suppose this is a query. I'm sure all of you are familiar with the aggregation type of queries and SQL in general, so all of you are comfortable with that. So this is a very simple query. So you can see here what is being asked. So I'm saying that select p dot category. Category is an attribute in the product table, and I'm trying to find out the category wise sales. So this is basically category wise sales. Okay, so the output of this would be like category 1 and the sale amount. And so on. Now here I have another query which is select L dot state and some sales from location L and sales S, where L dot, so this is join condition, and group by state. So another query, so this is state wise sales. Okay, so here the results would be like this: state 1 10,000, state 2 5,000, state 3 and something like this. So this is state wise sale, and this is a product wise category wise sales. So these are two queries that I want to execute, or these are, you can say, important queries or frequently asked queries. Now, as I told you, it is not possible for me that for every query QI that I have on my database, I have a corresponding Metallized view, right? It is not possible. So what we try to do is, right, so suppose I have some queries, say Q1, Q2, Q3, right, and so on. So Qn. So what I'll try to do is, say possibly I'll try to answer or I'll try to create a metallized view. I'll call it 1, 2 because it benefits queries 1 and 2, which help both queries Q1 and Q2 to execute faster using the concept of metallized views. So this view is designed in such a way that both these queries are benefited. Both Q1 and Q2 are benefited. Not so it is not that you cannot have a view, metallized view, which can 100% benefit both Q1 and Q2. That means your response times of this would be minimized. So all the work of Q1 is done in this view and Q2 is also done in this. So that is not possible. So suppose I am saying 50% of work of Q1 is done in this, already done in Metallized View 1, and say 60% of work of Q2 is already done in the Metallized View. So we need to design views, Metallized Views, in such a way which benefit not just one query but multiple queries, right? So that's the idea. Okay, so in this example now, I am now trying to, so one way could be that for this entire query I have a metallized view which I call as metallized view category, and for this I have another view, metallized view, which I call metallized view state. Okay, so this is the easiest option, right? But now you suppose that I have space only for one metallized view. Like suppose this takes say 200 MB of space and this takes say 300 MB of space. Okay, so I'm now saying that I have space only for I have only say 300 MB of space, right? So one option could be that I only store this view and do not store this view. So this query does not get benefited at all, the first query, and the second query gets 100% because the metallization for this. Okay, so now if I have a view, metallized view, which can benefit both the queries, say as I said 50% and 60%, but it takes only say 200 MB of space. So I would prefer that. So let us see now. So both queries require us to join the sales table with another table and aggregate the result. So you can see in both these In the first query, I'm joining the sales table with the product table, and in the second query, I'm joining the sales table with the location table. And then I'm doing some aggregation with respect to category in the first query and state in the second query. How can we use metallization to speed up these queries? Right, so let us look at the options. I gave you certain options, right? So let me just formally put them in the next slide. Okay. So pre-compute the two joins involved, so that is product and sales. So if I just do the joins involved, because joins, as you know, are expensive, right? So I would have one metallized view which will be, like, I'll write it here, metallized view 1, which would be product join sales, and I have another metallized view which is location join sales. So I can do this only now. So in the first query I would only need to do the group, the aggregation part, and similarly in the second one I will have to do only the aggregation part. The joins are already done, pre-computed. Pre-compute each query in its entirety, but I'm saying this is not an option because I don't have enough space for this. Or let us say we define the following view. So now we define another, we define a view which is like this. Actually, this should be a materialized view. So define a metallized view, or create a metallized view, total sales, which is PID, LID and total, that is product ID, location ID and total, as select from this, and I am doing a grouping by PID and LID. So what this would lead is that this would give me, this would have done, this query is some kind of aggregation, as you can see, on the products and on the locations. So this helps in speeding up these two queries which we have been talking about in the aggregation part. And the same view can be used for both the queries, right? Because both the queries would require aggregation. So the view total sales can be materialized and used instead of sales in our two examples. So what I do is, so instead of sales, I'm using, so let me clear the annotations. So what the system does with reference to the metadata, it replaces the sales. So what I have done is, in both the queries, I have replaced sales table in my queries with total sales. Okay, that's what I've done, and this is done in with reference to the metadata, right? And then what happens is that part of the aggregation is already done, right? And so you save on the aggregation part. You don't save on the join part, because join anyway you are carrying out in this. So now you are doing a join between product and total sales, and similarly location and total sales. And total sales, since it is aggregated, which will be a much smaller table than the sales table. So the join, so this join would be less expensive than the join P join S and L join S, right? Okay. So what happens, provided there is no aggregation, there is no sparsity failure while doing the aggregation, right? So you somehow save on the join also a little bit, and aggregation is taken care of partially, right? So that way you have defined a view which can benefit multiple queries. So that's what we do, because we cannot afford to have a metallized view for each query. So you cannot have a one-to-one correspondence between queries and metallized views, right? So that's why we need to club queries together and then define a view, metallized view, which can benefit each one of them, if not partially, right? Not fully. You cannot have a view which can benefit 100%, which can reduce the work, reduce all the work of multiple queries, right? So you have to define views which can partially benefit multiple queries. So that's what we are trying to do. So that's what. So I mentioned these two problems from the book, which would help you get some more insight into the problem of metallized views and how they help in actually reducing the computation costs of queries. Right. So with this, I end this section. In the next section, I'm going to talk about selection of views, and then I'm going to talk about maintenance and incremental maintenance. So this will take care of this module on view materialization. And then following this, the last strategy that we are going to talk about for query performance enhancement would be bitmap indexing. Thank you.